Welcome everyone, my name is Steve Turrisi. I'm the Director of Training and Technical Services at JL Audio. I am located in southern South Florida, just a few miles north of the main factory down in Miramar. I have with me Mr. Rob Haynes in Southern California. Say hello, Rob.
Hello everyone, good morning.
And over in Pittsburgh, Pennsylvania, we have Mr. Kevin Ferry. Say hi, Kevin.
Hello everybody.
Fantastic. So today's session is session 301 of our DSP amplifier course, and this is the one I think a lot of people have been waiting for. I'm going to caution everyone right now, I'm going to be very hard pressed to get this done in our usual claim of 30 to 45 minutes. And I know that we've run a little long on each one of them, but I'm almost certain to run long on this one, so I'll apologize in advance. The problem is there's a ton of content, and we want to share as much of it as we can. So bear with us. We'll get through it all together. So if you're watching from WebEx, over on the right-hand side of the screen, there's a little chat area. If you don't see that chat area, along the bottom of your screen, you should see some icons and things. You'll see something that looks like a chat bubble. Click on that, and you'll see the chat pop up. Kevin and Rob will be keeping an eye on that chat, and they'll answer any questions or comments that may come up. I will not be able to see any of those, so if you need to get my attention, direct it please to Kevin and or Rob, and they'll either flag me down or let you know whatever the answer may be. Similarly, on Facebook Live, both of them will be keeping an eye out on any comments that may come through or questions that come through on the chat there, so please go ahead and interact with them there as well. And without further ado, I'm going to start sharing my screen. Did I miss anything, guys? All right, so today we're going to get into advanced tuning practices. Again, this is the 301 course. If you've not seen any of the previous courses, some of this may be a bit of a challenge to follow along. We do a brief recap here at the very beginning of some of the tuning aspects, but some of the terminology and kind of what led us here have been covered at length, especially in the sessions like 103, 4, and 5, and then section 106, session 106 too did the tune click-through. We're not really going to talk about tune specifically today. We're going to talk about tuning instead of tune. This can be done pretty much with any software package. Obviously, we lean heavily on our own. So we're going to kind of get into a discussion about the different tools that we use to do tuning and kind of like I call it the truth behind the tools. And we're going to talk about how to look at the data and use the right tools to adjust whatever we're looking at. And I call it a new way to tune. It's really not a new way to tune. It's just maybe a different approach to tuning than some of us might be used to. And my comment there is time is on your side because most of this is focused on time. So before we start tuning, we have to remind ourselves of some of those earlier conversations of how to analyze the audio system. Before you can adjust it, you have to analyze it. So who remembers, and I am going to wait for an answer, who remembers some of the measurement tools that we use to analyze the system and the most common tools that we use? So let's wait for an answer. And again, Facebook is going to be a little lag behind, so I'll wait a couple extra seconds for an answer from either Facebook or a WebEx chat of what tools do we use to analyze audio systems. It's a bunch of answers. There's a specific one I'm looking for, or maybe a specific two.
RTA, WebEx is blowing up at once. Yeah, we got ears and RTA and more ears.
Ears. They know me too well. I am looking for ears, absolutely. We do have two ears that we can listen to, and it's a great way of evaluating an audio system. But when it comes to critical analysis, we strongly recommend doing some real analysis using microphones. And we had talked previously about how many microphones to use. Ultimately, what we're looking to do is we're looking for a way of capturing the data, analyzing the data, and potentially even sharing that data. So we want to use microphones with an RTA or an FFT or some way of looking at the audio system's responses and determining what we need to do. And we talked about where we're going to put those microphones, and we kind of talked about like moving a microphone around like a goof with the figure eight or whatever. And it's a really good thing to do. It just gets really tiring. So we would actually recommend maybe using a multiple microphone array. And in some follow-up conversation on some of the earlier sessions that we had done, we normally would recommend using a measurement system like REW. Well, REW doesn't allow multiple mics to be used all at the same time, so you would actually have to take measurements from multiple mics and then average them together. But the software allows you to do that, so it's not as fluid, but it's a pretty powerful tool to do some really neat things. Anyway, so we talked about all of that already, and we also talked about the method that we're going to do in terms of correcting the three pillars. And in our previous tuning session, session 201, A and B, we talked about using pillar 1, level, and pillar 2 for frequency response. Those are the two primary things that we do. And when it comes to doing pillar number 1, adjusting level, there's really only a couple of things that you could do. There's really not much to show you. You adjust the level until left and right or whatever match. All the different drivers will match. So the tools that we have there, like balance control, I guess is a real basic one, or you can actually use independent level control by the DSP, which is obviously what we probably want to do. When it comes to pillar 2, frequency response, we've talked at length about how we can use high pass and low pass filters to contour the frequency response, as well as using equalizers, parametric or graphic, whichever one makes you more comfortable. We recommend parametric because of its flexibility. But those are the two controls that we're likely to use to correct the pillar number 2, or the frequency response. And just as a reminder, the goal there was to get the channels to match. So here we're looking at 2 broadband channels, a left and a right as an example. And you notice the yellowish one looks different than the greenish one. So the goal of pillar 2 is to make a match. And, we talked about tuning to a target curve, and we're going to get back to that in just a moment. But ultimately, pillar 2 is that frequency response, making those 2 as close to each other as possible. That's the reminder there from what we did at the 10-minute tune or the basic tune, both for the mobile environment and the marine environment. So when we come back to the 3 pillars, the last one was phase or timing. Now, when it comes to this, it's all about relative phase, because phase is a measurement of time, and we want to know the relative interactions between a left and a right channel, or a mid-bass and a subwoofer, 2 separate things that we want to measure together and look at their timing response. So let's think about 2 ways that we can adjust just the timing aspect of an audio system. There's 2 answers I'm looking for, and I do want answers, so I'll wait for the Facebook people as well. So I need 2 things that we can use to adjust the timing of a signal. 2 specific answers that I'm looking for to adjust timing.
You brought up a good point while we're waiting here about it being relative to one, between 2 speakers, because if you just have one speaker and the timing's off on it, you never really know.
Yeah,
right?
who cares, right?
And to compare it to.
100%, so, Kevin, 100%.
We got a couple answers now. Polarity and delay from Neil and Scott.
Fantastic. I'm going to give you 75% correct on those. Since you gave 2 answers, I had to kind of average it. Phase, delay, absolutely. Polarity isn't really a time relationship. Remember, that was a directional relationship, and we are going to review that in just a few moments as well. So we're going to look at what happens with polarity. We often do kind of talk about it in the same context as phase, and I'm going to show you why that may be a little dangerous, but I love the answers, and I love that you remember delay. What is the other tool that we use? It's the one that so many people are confused by, and I can definitely understand why, but it's that weird thing everyone says, well, what do you do with this particular feature? And this is what you do with it. It's a phase or timing relationship that's a little special. You getting anything? I hear some laughter.
I'm just I was laughing at it being special.
Oh, it's special.
Does it allow things to pass through it?
It does. It pretty much allows all things to pass through it. It's the all-pass filter. Very good, everybody. Thank you for paying attention in the previous sessions. So an all-pass filter is also what's known as a phase EQ, and it's sort of, as you'll see in just a few minutes, we're going to explore exactly what an all-pass filter will do for us. But it does allow some adjustment of only the phase domain. It really doesn't affect frequency response. Only when, as Kevin was just mentioning, only when the 2 channels might interact with each other. So we're going to come back to that in a little bit. But these are the tools that we use, and they're kind of what they do. You know how to adjust level by channel. You know how to adjust frequency response with HP and LP filters, as well as bandpass filters, right? And a parametric EQ or whatever kind of EQ. Those are all things that you know on frequency response. And now in the pillar number 3, phase or timing, we have delay, and we have the phase EQ or all-pass filters. So let's get into it a little bit deeper. So in order to do analysis of phase and timing, we have to be able to adjust for differences in distance. And there's a very fast, cheap, and easy way of doing this, and it's a tape measure. And in one of our earlier sessions, it was covered that we can use a tape measure to enter in distances into Tune software, and it'll automatically calculate what those distances are relative to each other. And it does it very simply. You can either enter the distances from a tape measure, or you could calculate out what the milliseconds of delay would be. Milliseconds of delay. That's time. Or you can put that directly into the software, and there's a lot of different ways of doing that. Tune makes it easy. Other software, you can actually just do some simple math and figure all that stuff out. However, there's another way that's a bit more involved, and some people would argue that it's more accurate, and depending on what you're going to do with it, it can be more accurate, and it's something called impulse response. Now, what an impulse response is really what the name implies. It's when a speaker is responding to a known impulse. To capture this accurately, you're going to need a special sound card. You're going to need a way of referencing time. So you need some equipment, some understanding, and some time and patience. You see what we did there? Time, patience.
This is some bad timing on these jokes right now.
Bad timing. Oh my God, they just write themselves. Anyway, so in order to take impulse response measurements, you need to know when the impulse starts and then when something responds. So imagine if you sent a signal out at the same time to two different places. One place it goes right back into the measurement system, and the other place goes out to a microphone. It goes out to your device that you're testing. So it goes effectively into your aux input or into your source unit. It goes through the source unit, out the output of the source unit into, let's say, a crossover, an EQ, an amplifier, and then it goes to the speaker, and then from the speaker it goes flying through the air to the microphone. Well, all of those different things, in some cases they're all built into one, like in a DSP-based amplifier, the crossover, the EQ, and all that other stuff is built in with the amplifier. All of those things will affect the electrical time, and then of course the speaker is going to have time of flight from the speaker to the microphone. So what it's going to do is it's going to say, okay, the short piece of wire, that was instantaneous, but everything else is now going to be delayed. And that is going to show you what the impulse response is for the driver relative to the short piece of wire. Knowing exactly what that is allows you to line up all the impulse responses and then analyze their time responses more accurately. You'll get close with the tape measure, but not close enough for detailed analysis. If that's what you want to do, impulse is the name of the game. Now, once you get everything set up, it's not that hard. Once your measurement system has really been established, you're good to go. You don't have to do this every single time or recalibrating all this stuff. If your measurement system stays the same, it's pretty simple to do. So once you get it all good to go, all this benefit of detailed analysis of phase can take place. All right, so now we talked about timing, and we're going to talk about what the tools that we use are actually going to do. So I call this a look behind the tools. We're going to look at what actually happens when you use an EQ, what you actually are doing with the high pass and low pass filter, delay, polarity, all pass, all of it. We're going to cover every single bit of it. But in order for any of this to make sense, we need to be able to analyze the data very carefully. So we're going to establish a couple of reference points. So my thought here is if you know what the reference is, you'll be able to see a change from the reference. So that when we actually look at real measurements, you'll know what the reference was, and you'll be able to see those deviations a little bit more clearly. So what we're going to do is we're going to look at changes in magnitude response or frequency response. We're going to look for changes in phase. Ready? Here we go. You've probably seen something like this before. This is basically going to be our magnitude response graph. And along the bottom edge, we have frequency. We have low frequencies on the left and higher frequencies on the right. This is plotted on a logarithmic scale, so it kind of mimics the way our hearing picks up on things. So lows on the left, highs on the right. Everything in the middle is the middle stuff, and we'll break that down as we go forward. And we do this based on its amplitude, or how loud it is. In earlier sessions, we did cover these terms in detail, so if you need to, check out 103, 104, and 105, I think is the sessions. But those sessions cover these basic terms. All right, so that's what we're going to do to analyze frequency response. On the bottom, we're going to look at phase response. Now, what's interesting here is the frequency is still the same. Low frequency is on the left, higher frequencies on the right, with everything else across in the middle. So frequency remains consistent, but on the left side, we're going to look at phase. Now here, it's not so much like amplitude. Here's our degrees of phase, and that middle line is 0 degrees. So 0 degrees is, and again, it's just a reference. These numbers don't matter much in and of themselves. What matters is relational things, and we'll get more on that in just a moment. On the top end of the screen, you'll see that it's 180 degrees up there, and on the bottom, it's minus 180. Remember that we kind of talked about this sort of like a circle, so 180 and minus 180. It's basically 360 degrees around. Imagine if you're looking at a cylinder on its edge, in these days, paper towel roll, right? So you got a paper towel roll, and you're looking at just one side of it. It continues on the other side, and it goes all the way around, but you're only looking at a flat portion of it. So this is wrapping around. So you'll see that a little bit more in just a moment. So those are the two graphs that we're going to look at, amplitude and phase. So let's get into it. Equalizers. Equalizers are not just frequency adjustments. We focus on that because it's the easiest thing for our brain to kind of capture. So we focus on the frequency aspect of it, but there is a corresponding change in the phase response that happens as well. Now you may not have known that, and maybe you did know that, but I'm going to show it to you in detail. So if we take a look at this, on the top, again, is our frequency response, and you see that we have a cut that's been applied. We're pulling out some information around a particular frequency. And on the bottom, you'll see what's happening to the phase response. It kind of is dipping below 0, and then it's going back above 0, and then kind of flattening out again. It's causing a bit of a ripple in the phase response. And it's doing that centered right around, in this case, 1,000 hertz, just because it was an easy number to work with. So in this case, you can kind of see what's happening. A cut is causing this specific shape in the phase response. Now, if we were to change that to a boost, it would have the same effect, only in reverse. Instead of going down first and then up, it goes up first and then down. That's not important. Just know that the equalizer is also causing a change in the phase response. It's sort of looking at two sides of the same coin. Each one is related to the other. So that is it's a fairly wide EQ band, in terms of Q. And remember when we talked about parametric EQs, you can adjust it to be wide or narrow. If we did make this narrow, it has a corresponding change in the phase response. This is what that would look like. So here's a cut at the same frequency and of the same amplitude, but now you see that it's narrower. The Q is narrower, and so is our phase ripple. The phase ripple is also more narrow. So that's what's happening when you work with an EQ. Done. Next, high pass and low pass filters. Let's see what happens behind the scenes. Well, phase shift is going to depend on filter slope and type. Steeper slopes will create more of a phase shift, and it gets a little difficult to kind of talk about. So we're going to focus in on one particular type. Just note that the different types will change the shape slightly and how it actually goes wrapping around, as you'll see in just a moment. So the different filter types like Linkwitz-Riley or Butterworth will look a little different, but ultimately they all have very similar behavior to what you see here. So on the top, you notice this is a traditional high-pass filter, and this one said it looks like about 5,000 hertz, right? This one happens to be a 24 dB per octave Linkwitz-Riley filter, and you'll notice on the bottom that there's a phase wrap. It goes, it's starting from left to right. It goes down to about the 5K point, and that's a minus 180. And then it wraps around to the top part where it's at plus 180, and it continues to slope back down to the reference line. That phase wrap is indicative of what's happening at a filter frequency. Here it's a high pass filter. But here's the crazy thing. The phase response looks the same if you do a low pass. It's exactly the same thing. So you can see by those wraps that that's a filter frequency of a high pass or low pass. And maybe something else. We'll come back to that in a moment. So that basically is a summary of what's happening with high and low pass filters. We still good, everyone? Any major?
And Steve, that looks like that's a 24 dB Linkwitz-Riley.
It is very good. You must have known something about that, huh?
Just looking to clarify.
Uh-huh.
Is that a small plug for your tech tip video on YouTube?
It sounds like one.
I was just wanting to let everybody know that was listening in what we were looking at, because we discussed that depending on the slope and the type, the phase relationship could vary between one another. So I just wanted to let everybody know which ones we were looking at. But I knew what I was looking at because of that video.
Right on. So the phase will look different between a Butterworth and a Linkwitz-Riley. It'll look different between a 6, 12, 18, 24, 36, 48. Whatever the slope is will also change that shape. But in general, what you're looking for is that it will almost always wrap. With rare exceptions, it'll almost always wrap in a manner that you're looking at here. All right, cool. Give Facebook guys a chance to get caught up in case there's anything I needed to address. Now we're going to move on to delay. Now, the cool thing about delay is it sort of gets a little bit easier in a way because it only impacts time and phase. It doesn't affect frequency response at all, not by itself. Remember, what we're looking at here is individual drivers or individual measurements of a sound source, right? So phase is the only thing affected by delay. It does not alter the magnitude of response. So instead of showing two graphs now, I'm only going to show one because nothing changes on frequency. This shows a delay applied. And the delay, let me check my notes here. We can actually we're going to do some math and figure this out together. So the curve that you see there, it starts off at the 0 line and it kind of slopes down and to the right. That basically means that things are getting delayed. There is also something, if you did your impulse response measurements wrong, it would go up and to the right, and that would show that something's arriving early. So almost, well, if you're doing it the way we recommend, your phase responses will almost always wrap down into the down into the right. Down into the right is a delay, which is okay. It's always going to be there. Now, if anyone remembers, there's a way that we can actually determine time using a formula. Who remembers the time equation? If anyone gets this, I'll be really impressed.
I think it has something to do with frequency.
Yeah, it sure does. And we can see frequency on here. We can't really see delay, though. We'd have to calculate it. So if we're looking to find out what the delay value is, that's the period of the sine wave, or a period of the waveform. And we could see frequency. So I'll let you guys off the hook. So the formula for period is 1 over frequency. And what we can do here is we can replace the 1 over a window of time. And I'll show you what I mean by that. So top center of the screen there, you'll see that's a waveform. Whatever the waveform is, the frequency at this particular point doesn't matter. But let's take a look at this yellow line. That particular aspect of the time of the phase response of this system corresponds to 1 full wavelength, and I can show you this. If you take a look at this point here, that's effectively 0 or 180 in this case, right? So remember, the top of the chart is 180 degrees, the bottom is minus 180 with 0 at the center. So 0 and minus 180 slash 180 is the same point, it's just on the opposite side, right? So we'll start off at the 0 point or the 180 point up here, and that's at 5,000 hertz, right? If we go down to the center point, that's crossing in our particular graph right at the 0 phase mark, right? And that's at 10,000 hertz. And then we go down to this point, that's minus 180, so it wrapped around the cylinder, so to speak. So if we're looking at 5K, then 10K, then 15K, what we could do is we could look at the value of the phase at the highest frequency, the value of the phase at the lowest frequency, right? And divide it by 360, because that's what the cylinder is. And that's how we can actually determine what the delay is. So who wants to do that math? Nobody does. It's too early in the morning or too late in the afternoon, depending where you are.
Sorry, you're cutting out over here. I can't.
Exactly, right? All right, so the yellow line, it starts at 180 at the top, and it's minus 180 at the bottom. So if we do phase high and phase low, 180 at the top, minus 180 at the bottom. If you subtract that, what do you get? The answer is 1. And the formula tells us that since it's 1 wavelength, it's divided by 360, it's going to give you 1, right? So basically we have 1 at the top. You with me? 1 at the top. The high frequency is 15K, low frequency is 5K. If you do the math, 15K minus 5K gives us 10K. We see that in the middle. So basically our period or our time is 1 over frequency. We have that number 1 on the top already, and our frequency is 10K. So what is 1 divided by 10,000? If you do the quick math, it winds up to be 0.0001. That's 0.1 millisecond. So just so you know, 0.001 is 1 millisecond, 0.01 is 10 milliseconds, and so on. We good? Everyone good?
We seem good here.
Excellent. So 0.1 would be 1 millisecond. All right. So that's how you can do time analysis looking at a phase trace. This isn't critical. I just thought it was interesting to do a correlation between period and phase and all of this. You see where it's all coming together. So now what we're going to do is we're going to apply more delay. In this case, we put 0.1 millisecond worth of delay. Now we're going to increase that. If you wanted to do the math here, we worked this out. It's basically that wrap is going to show up here, and that crossing at 0 is going to take place at 1,000 hertz, and that's going to give us 0.001 seconds or 1 millisecond. All right. And then here we do it more. Additional delay. You'll notice what's happening is that everything's kind of walking from the right side of the screen to the left side of the screen. That wrap that I've been focusing on, this yellow line, you could see that more delay makes that simply move from the right side of the screen to the left side of the screen. So higher amounts of delay will affect more and more frequencies above that particular point. But the shape and look of it remains consistent. That's delay. Now polarity. Now I tripped up some buddies of mine by asking what things affect time. Polarity only impacts the time/phase response, but it doesn't actually shift time. It looks like it, but it's not. It affects the direction. To illustrate this, let's take a look at this function here. This is the phase response. I'm going to wait for an answer. What caused this type of phase response? What do you think probably caused this type of phase response?
Frequency.
You're only looking at phase. So some filter has been applied that changed something. I can see it here on the phase response. Where have we seen a little shape like that where it kind of dips down and it goes back up to the 0 and then it humps and then it comes back down to the 0 line? Jeopardy music, please.
Adam's saying an all-pass filter.
No, you're not there yet, Adam. Hang on. I'll cue you when the time's right.
So if it was an all-pass filter, it wouldn't be affecting the frequency response.
Correct. Well, you can't see frequency response.
We have some answers on Facebook.
Chris says a frequency cut.
Ooh.
EQ.
There we go. That's what we're looking for, EQ. So I'm sorry. So yes, it's an EQ that has been cut, right? So the cut, we know this because the phase response goes down first and then up. If it was a boost, it would go up first and then down. So it's really great that you start training your eyes to look at these changes in the phase response and what may be the corresponding change in frequency response. Now, you should always be looking at those two together if you're doing analysis, because there are some things that will only affect phase and not frequency. So it's not always going to be an EQ. In this case, it was. It was an EQ cut, moderate Q. So you got that answer. Very good. If we were to flip the polarity on this, and flipping the polarity is kind of like this, taking the plus from a speaker and putting it on the minus, and the minus from it and putting it on the plus, and just kind of flipping it. It's going to change the direction of it. And if I do this, you can see exactly what happened. Where it was at the 0 line, it split it. And it's still going down first and then up, but now it continues up from the bottom part and then goes back down. So basically what is flipped it. We split it, so instead of being at 0, it's on the other side of the cylinder. We flipped the polarity. But everything else about the time aspect is exactly the same. It's just the direction of it that has shifted. Instead of being in the middle, it's at the top and bottom. So it's the same effective thing. It's not actually a time shift. It's more of a positional shift or a directional shift. That's it. So again, to remind you, the 0 dB was at the middle, and now we're basically splitting it. Minus 180 and 180 are effectively the same point. I can't illustrate. If I did this with a flat line, you wouldn't be able to see it because it would either be a line across the middle or two lines top and bottom. It's the same line. So creating that little wiggle there allows us to see what polarity flipping does. Which leads us to the all-pass filter. This only affects the time or phase domain. It does not affect frequency. It functions virtually identical to a high pass or a low pass filter, but it does not alter the frequencies. This type of filter does not change the frequency response, but it does the same effective thing on the phase response that a high pass filter would do or a low pass filter would do. But instead of high passing or low passing, it is all passing. All frequencies are passing through it, but it's still applying the same type of phase shift that we've seen from a high pass or a low pass filter. So it's going to have a Q shape, and we talked about the different types of crossovers, like a Lincoln-Riley or a Butterworth, and the different slopes, 2412, whatever, of those crossovers, and we talked about them changing the shape of the phase. And the same would be true here on an all-pass filter. So let's go ahead and take a look at one. Again, there's no change on the frequency response, so we're not even going to look at that. We're only going to look at phase. So the phase response on this particular filter, it goes down and it wraps around to the top. And we just talked about how this looks exactly the same as a typical high-pass or low-pass filter. And if you remember from moments ago, high-pass and low-pass filters from the phase side of things always look the same. So if it was a high pass, it had a certain look, and if it was a low pass, it had a certain look. Well, the same could be said here. So if we take a look at this, that's what the crossover did, or the high pass or low pass filter did. You'll notice that those two white lines have a very similar shape to the two split, or the one green line that has been split. It's at the same frequency, same type of shape to it. It's doing the same thing. It's wrapping the phase. So looking at this, we're going to start now changing the Q. And it's going to change the shape of the all-pass filter, or the wrap that we see here. So if we increase the Q, you'll see that it got a little tighter around that dotted line. Again, it's centered at 1K. And if we make it a little tighter still, it's a higher Q value and an even tighter. So as we start adding, as we start adjusting the Q, we start pulling that phase wrap in closer to where that central point is. And as a comparison, here's those several different Q filtered all pass responses. And you see the higher Q starts walking closer and closer to the line. So the reason for all of this is we're going to let the data guide our eyes. So when we know what to look for, if we know what the tools are doing, we know which one to apply when we see some weirdness and or some issues that need to be addressed when we do data analysis. I kind of think of it this way: if you're looking at a piece of wood that's got something sticking out of it, if it's got a little circle thing on it and a plus sign on the head of it, you could probably use a hammer and hit that thing in there, but it's not the right tool. You're looking for a screwdriver, right? If it was just flat at the top and didn't have the little circular lines on it, you just use a hammer. You need to be able to analyze the situation and pick the right tool. So let the data guide you. And we're going to do the same thing that we did in the basic tune. And we're going to set filters and stuff like that based on targets. So when we talked about tuning to a target curve, we're going to get this a little bit more detailed. So if we do a multi-way system where we have tweeters, mid-range, mid-bass, and subwoofers, we're going to look at the data for each one of those and apply filters based on what we're looking at. High pass, low pass, band pass, whatever the case may be. Once we set those filters, then we'll apply EQs to the target curves. Stay with me, I'm getting somewhere. These are the target curves that we have been talking about. This is for basically a full range or a full spectrum. It's got the low frequencies on the left, it transitions through the mid-bass, through the mid-range, and then to the higher frequencies. And if you're dealing with like a coaxial with a subwoofer, you can use everything from 1 point higher and then 1 point lower. If you're using a multi-way system, you're going to look at each one of those individually. That's exactly what we're going to do. A multi-way system is really a sum of all those parts, so we're going to dial in each one of those parts. To break that up for you, let's take a look at this particular target curve and each of those band-specific target curves that will form that. So if you kind of look at this, we have a white one that's clearly our subwoofer. It's all the energies at the lower frequencies. Next up, we have like a light gray line or a dark gray, whatever, that's kind of a grayish line. That's our mid-bass driver, and that's going to couple with the subwoofer as well as the green line, which is our mid-range driver. And you'll notice that even though they're rolling off as they cross over each other, they're going to sum to meet that yellow line together. They're going to create the target yellow line by summing together at those crossover points. The green mid-range will transition over to the purple high pass as well. In this case, it would be a tweeter. And again, they'll sum to give the shape of that yellow curve and then taper off. We're going to start off focusing on that purple line, that tweeter. So what I've done here is I've ran signal through a tweeter in an application. And just for the record, I have no idea why I have all that noise at low frequency. I think it was something wrong with I did this in my driveway, so it's probably some weird noises, the ground vibrating or something. I have no idea.
Is your neighbor cutting his grass?
It might have been, because that happens, right? So, but I know that a tweeter is not going to be producing significant content down at 40 hertz, so I can effectively ignore that. It's not a real measurement. But that white line that you see there is the measured response of the tweeter. Now, I remember when we were doing the basic tune, we talked about letting the measured response allow us to pick our target curve. Well, this one you can see that the high frequencies are rolling off fairly aggressively. I still picked something that had that gentle taper, but even this one is dropping off even more. We'll come back to that in just a moment. The first thing I need to do is get rid of some of the lower frequencies to match up the target curve. The reason for this is even though this particular tweeter can have some significant output down to a lower frequency, we need to make sure it's going to couple up with the mid-range. And the mid-range and the purple line, the green and the purple line, if you remember, they're going to sum together if we match this target curve. So what we're going to do is we're going to apply whatever filter we need. Lincoln Riley, Butterworth, it doesn't matter. Pick whatever slope you need to make the frequency response match the purple trace. When I did this, I put on whatever it was. I honestly don't even have a note on it, and I wound up at this. So this pinkish trace here is an applied high-pass filter that is trying to mimic the purple one. Now, if you notice, there's a bit of a spike there that was there before, and it's still there now, that kind of deviates above the target curve. Remember what we learned with the basic tune. If you need to, position everything on the lower end of the measurement so that when you use cut, you come down to it. And this is a good example of what we'd be doing there. So that is basically what we're looking at. Let's clean it up. So those are the two things we're looking at. Ignore the crap down low. The yellow curve is what our overall target is, and the purple one is the tweeter's target. So now we're going to apply some equalization. And when I do that, I'm able to get rid of that peak pretty effectively. I was also able to use a shelf filter and boost up some of that high frequency to get much closer to what that target curve was going to look like. So I would say in this case, the tweeter is pretty close to where we need it to be. Through the, so there, sorry, I forgot to click. So there we go. We're pretty locked in. We're going to do the same thing through the magic of technology on all the drivers in the system. So basically I applied low pass filter on the mid-range driver and a high pass filter on the mid-range. A low pass on the mid-bass and a high pass on the mid-bass and then a low pass on the subwoofer. And I did whatever equalization was necessary to try to get those as close to those lines as possible. It's not perfect, but that's okay. It's simply a matter of matching those targets as close as we can before we actually start doing some more detailed analysis. That was one channel, left channel. This is the right channel. And you see we did the same type of thing. They're different, but they're close. So after this, we'll get back to things, but we're going to look at the phase response next. Everything that we just talked about is a more detailed version of that basic tune. You could do exactly the same thing as a basic tune. It's just going to take you longer. So that's that. Now let's look at phase. Time needs a reference. In order to do detailed time analysis, you need a reference point. And we talked about this. We talked about using a tape measure. And that's good for time of flight compensation, but it does nothing for any of those unseen delays. Now, in most cases, an impulse response is going to show you that. Not all, but most cases. But no matter what, an impulse response measurement is vital for detailed analysis of phase. Slight deviations in impulse response will mess up your phase response readings. And when you're looking at relative differences, you need them all to line up. Because phase has a couple of components. Phase shift is what we normally will talk about. And everything we've looked at so far is a phase shift. And it's a change within a single device or system. And this does not change frequency response. And it's considered absolute phase because it's in a single confined system. And this is what Kevin was talking about when we first started out. If you're only looking at a single sound source, a single point, the phase response is pretty much irrelevant. It really doesn't matter very much at all. It might be interesting to look at. And if you know what you're looking at with other things, you might be able to look at it and say, that's kind of intriguing. But by itself, it's basically meaningless to us when we're tuning a system. Phase offset, however, is far more important to us. This is the difference between phase of different drivers. So it's the phase change between speakers, like a tweeter and a mid-range, or a mid-range and a mid-bass, or a left channel and a right channel. And now this may change the frequency response because of the interactions of that. Now we talked in one of the earlier sessions where we showed the difference between polarity and phase, and we talked about the phase difference being in time. And if we had the interactions that lined up, we would either gain or not gain output when we combine the voltages. So that's what we're talking about here. Is the timing relationship between these two sources is relative phase. And this is what we care about most, especially at lower frequencies. There is some debate on how low is low. In general, I would say from 1 to 2,000 hertz and down is where we're really going to be looking at the phase response much more critically. As you start getting significantly above 2,000, 3,000 hertz, something changes that makes phase maybe not quite as important. You can still analyze it. It gets harder to analyze, but it becomes, in my opinion, slightly less important. Anyone have any idea why? What changes at higher frequencies that makes phase or the relationship between two sources maybe not as important to our hearing? That's a clue.
I know.
Yeah. If we're listening to relative differences between left and right, if we're listening to relative differences between left and right, higher frequencies don't matter as much, in this man's opinion, because the wavelengths associated with higher frequencies are less than the width between the two measurement systems. So the relationship between those wavelengths becomes less and less important as you go higher and higher. It doesn't mean that they cannot be analyzed effectively. They certainly can be. And if you wanted to, you could look at phase. But I would contend that once you get it good from about 2,000 hertz and lower, you should listen to what's happening at higher frequencies rather than looking at it. because that's how the system's going to present itself, and most of those differences will present at those higher frequencies. So that's why when we talked with the basic tune, I said, let's get to listening as quickly as possible. Here again, I'm going to do the same thing. Let's focus at lower frequencies and get to listening as fast as possible. So let's analyze phase. I picked this up in a book by Bob McCarthy. He wrote a book called Sound Systems, Design and Optimization or something like that. And he wrote that phase is a radial function that can set our heads spinning when it comes to reading the 2D charts. And we have looked at those charts already, and that does set your head spinning. So let's do it some more. How about it, right? Let's just dive in and do exactly that. So let's look at this system here. This is the left channel of an audio system. Doesn't matter which one. It's just the left channel. And as we talked about earlier, the top graph is our magnitude response or our frequency response. And you could see it's got some wiggles and stuff going on there. There's a pretty nasty dip somewhere. I don't know, it looks about 1,000 hertz, whatever it is. It almost doesn't matter. On the bottom is the phase response of that. And again, by itself, it's just interesting to look at. And you can see that the wraps are going down and to the right. So there is some delay associated with this relative to a straight line. Right, so there's been delay applied somewhere along the line. That might have been delay from our signal processor. It might have been delay through the amplifier or the electronics. It doesn't matter. We don't know. And honestly, by itself, we don't care. It's only when we compare it to the right channel. Now, if you look at this very quickly, and I can't imagine you memorize what you saw on the previous screen, but the green line for the right channel is a bit different than the left channel. So we have some work to do in terms of equalization to make those two match. Remember that pillar? The phase response also kind of looks similar. It's wrapping down and to the right, exactly like Steve said it's supposed to be. But there are differences between left and right. Let's look at them. The orange trace was your left, the green trace is your right. Frequency response, you could see that we didn't quite nail it. There's still some deviations there. And if you look at the phase response, if you look down low, they line up pretty darn good. That's kind of low frequency though. It's probably out of band for these particular drivers. And if you look at the frequency response, you can see it's kind of already rolling off and starting to lose some of that amplitude. So that's not that important, but up high it is. And here, it looks like it's pretty well lined up. Not perfect again. Now here's something interesting to pay attention to. It's kind of off script a little bit, but you'll notice looking at the phase response, there's some deviations between the green and the orange. And you'll also notice that in the frequency response, there's some deviations between the green and the orange. Where the green and orange are closer in the phase response, they're also closer in the magnitude response. What was that? Oh, I know what that was. So if you look at that, there's a direct correlation between the phase traces and the magnitude traces that show you that we're looking at two sides of the same coin. So if they were the same, they're going to line up perfectly. So at high frequencies, they're pretty close. And at low frequencies, they're pretty close. But what the heck's going on here in the middle? The orange one's way up here, and the green one's way down there. Something's not right. They seem to line up in frequency response, measured by themselves. But if we were to play those together, probably not going to be the same. So, take a look at that. Now, I want to point out a couple of interesting things here. I'm not saying this is what's going on with these particular traces, but you can start seeing shapes that we saw earlier. If you look at the shape on the top there, that frequency response, you see it kind of looks like a cut on an EQ. Remember the cut on an EQ where it kind of goes down like that? And if you look at the phase response on the green trace here, if you look at the phase response on the bottom, you'll see that it's got that down, then up, then down wiggle, just like we had on the EQ. So you can kind of see here that the phase response and frequency response are directly related. Whether we caused those problems or something else did, you will see similarities. Again, know what tool to use to correct for each one of these things. In this case, if we wanted to compensate for that, we can use an EQ to boost up that cut to change the shape and get the shape closer to zero. Cool, isn't it? Additionally, we could look at these phase wraps and see the similarity to the delay. Remember that yellow line? That yellow line kind of shows how the delay is marching from the higher frequencies to the lower frequencies, and you can kind of see what's happening with how much delay is really there, the number of milliseconds. You can kind of mentally get a vision of all of that. All right, so that's that stuff there. This is a combined response where basically we're looking at left and right combined. That's the blue trace on the top. So the frequency response has been combined on the top. You can look at the phase response of that trace. It starts getting a little messy, so I'm going to start cleaning this up as I get a little bit more detailed analysis going. I want you to look at what's going on in the middle there. We've taken a left speaker and a right speaker and we've added them together. We would expect that these two speakers would add to a higher value, but they don't. There's something causing them to not produce additional output. In fact, we're getting less output. Think about what might be causing that. And while you're thinking, let's take a look at what's going on high and low. The lower frequencies did get louder when we combined them. The higher frequencies did get louder when we combined them. Let's take a look at down here in the phase responses of the two drivers. Remember the orange and the green? In the middle area where that center is being pulled out, the two traces don't line up. They're out of phase at that particular point. This is what the combined trace looks like, just as a reference. So now here's where it gets really messy, and I apologize, and I promise I'll clean it up. I flipped the polarity to try to improve what's going on because it's obvious that they're doing something opposite in the middle. And it helped. Take a look. Now we have an increase in output right in that middle area. That's fantastic. But what happened up high and down low? Now we have a reduction up high and down low. And if you remember some of the details that we talked about early in our course, we talked about if you have one speaker with the same amount of power and you add another speaker, we gain 3 dB. But in this case, it's not just a speaker, it's one system, and we added another system. So we would still gain 3 dB, but we also doubled power. So we should see, if everything is perfect, we should see 6 dB worth of increase. 3 for doubling our piston area, and 3 for doubling our power. Well, we may not get perfect on that because this is a dynamic system and it's going to be all over the map, but we should not see significant cancellations or loss of energy. And in this position, we do. We are seeing a dropout at low frequency and a dropout at high frequency, but we got better in the middle. Now, if there was only a way that we could take this amount of energy and flip the polarity or the timing reference only in a certain area of frequencies, but not change the frequency response. If there was only some tool that we had in our toolbox that would allow some phase adjustment over a certain range of frequencies, it's not going to pass anything different. It's not going to just pass highs or lows. It might pass all of that. What filter might we apply to only affect the middle frequencies and not affect those high and low frequencies? Have I given enough hints yet? Do we have an answer yet?
We got Scott and Chris are with all pass filters.
Fantastic, exactly. An all pass filter will allow us to alter the phase response in that middle area without affecting it at the higher frequencies or lower frequencies. So if we take a look here, this is what we have. We have a peak and then we have those two dropouts. What we want is to bring that back up. Right? So what we want is sort of a combination of these two graphs right here. An all-pass filter set correctly gives us this. And it's exactly what we want. We don't lose energy at high and low. We don't lose energy in the middle. An all-pass filter allows us to alter the phase relationship between the drivers or the systems, whatever the case may be, to line them up the way we need them to. And you can look at the phase traces relative to where they were before. This is exactly why we want to be able to analyze phase response. The truth is, guys, you could probably do some of this work by only looking at the frequency response or only looking at the magnitude response. When you combine the two channels, if you see that there's a dip in the middle, you probably need an all-pass filter. By looking at the phase response, you can get a better idea of where to put that filter and how much Q or what the actual shape of that needs to be. So looking at phase is faster, I would contend easier, and ultimately it can be a lot better than just looking at the magnitude response. Magnitude response can get you close. Phase response is going to get you dialed in. Phase is the key. So, sorry, I get a little excited about that. We're going to move on. Now that we've got the phase response of the main speakers lined up together as close as we reasonably want, let's just accept where it is right now. So that's our combined magnitude response, is that grayish, whitish line, whatever you want to call that. And now what we're going to do is we're going to add in a subwoofer. So here's the subwoofer, and here's the main speakers, right? So we're going to look at that. And you can look at the phase responses and just bear in mind bandwidth, right? So the subwoofer, what happens above a certain point, typically around 80 hertz or so, you can almost ignore in terms of phase. Similar with the high pass drivers. Anything that's high pass below the lowest filter frequency, you don't really have to look at phase all that much, but you do need to look where they overlap. That crossover point is what's going to matter. So the green and the pink, when we combine them together, we get this gold line. And the gold line, if you look carefully, it's not adding very well around that crossover point. This area right here, we're not seeing an addition of energy as we would expect by adding two sources together. They seem to be out of time. Now, one thing that we did before, the first thing we did was that polarity inversion. Now, polarity inversion we know is not going to affect the frequency response, so why don't we just give that a try? Here we see the subwoofer both in polarity and out of polarity. And if you look really carefully at the frequency response on the top, you will still see the red line exactly overlaid by this purpley whitish line, whatever color you want to call that. But if you look at the phase response at low frequencies is exactly what we'd expect. It's exactly flipped. So where it was 0 before, it's either 180 or minus 180. Where it was minus 180 or 180, it's now 0. And everything in between, it perfectly tracks out of polarity. So if we do this, so if like take a look at that one versus that. The whitish purplish line is at 0 and the red one is at minus 180. It's the same point, it's just opposite direction at this point. So now we're going to combine that with the main speakers and look what we get. Hey, it helped. That's fantastic. Right there, we were down there before when we combined it, and now we're up here. We gained our energy back by flipping the polarity. That helped. It doesn't matter what the pluses and minuses are. What matters is what's actually happening. The phase is better, and the magnitude is better. But I think there's more. I think we could get more. Before we do that, let's look at those original phase traces down there. That's the way they were, and now this is the way they are. You can see that they're lining up a lot better in that transitional region. They're a lot closer than they were. So what I want to do now is I want to see if I can get even more out of this system because I'm excited. I got some good stuff going on. The polarity really helped. My subwoofers and my mid-bass drivers are much more cohesive. They're combining really nicely. But I'm looking at that and I'm still seeing right where that gold arrow is. If you look down in the phase response, you could see that there's still some deviations there. I wonder if we could get better. So let's take a look at this complete jumbled mess of data. So if you look, you can see a whole bunch of different traces going on. Now I'm going to start peeling back a little bit and getting dialed in on the ones that I really care about. The ones I really care about are these. The orange one is what I want. So that's the orange is the sum response of the main and the sub. The red trace is the one with the inverted subwoofer, right? We flip the polarity. And now if we look at that carefully, if we look at the orange response, that orange line compared to this red line, that's the inverted sub. If we look at those two responses, what tool can we use that will cause the phase response to shift down and to the left, back into the left, down and to the left? What can we do to the orange trace to get it closer to the red trace of the subwoofer? What thing can we do? Now, we don't want to mess with the frequency response because that looks pretty good from our general purposes. We just want to combine these two better. We want to make sure that they line up better at that particular point. What can we do to change orange and shift it down and left?
It's nobody yet on here.
Boy, there's a bit of a delay between what I say and Facebook, right? So we might want to wait for that delay for the Facebook people. Did anyone deal with anything?
We have delay on Facebook.
Fantastic. Leave it to the Facebook crew. Yes, if we add some delay to the main speakers, we can actually start getting, to the subwoofer, we can start getting that phase trace to line up. So that's what we're looking for, right? That was where it was. That's where it is. We've lined them up. Now look at the magnitude response. The magnitude response of that new light gray color is actually higher than any of them before. We've made a much better transition from the subwoofer to the mid-bass driver, first by a polarity inversion, and then by adding some additional delay to make those phase traces line up. I would contend that if you were only looking at the magnitude response and you flipped the polarity and said, aha, I've got it, perfect. No. There was more to get. And if you really dial in, it's going to be hard because you guys are sitting at a screen, subset of my screen. But if you zoomed in, you would see that we gained about 2 dB in the 40 to 60 hertz region. 2 dB is almost 60% more effective power from the system. You gained about 60% more energy, roughly, in that region because you were able to look at the phase traces and not just the magnitude. You would never have known to add delay to the sub to gain that additional output. Phase is where it's at. It's about time that we covered it, right? But ultimately, none of this matters until you listen to it. You gotta listen. we may have screwed it up. We may have made some changes that didn't work all that well. I'm willing to bet if you analyze phase very carefully and you make the appropriate changes by knowing what tools are in your tool set to adjust all of those things. Is it a high pass filter? Is it an EQ? Is it an all pass filter? Is it delay? Is it polarity? You know what these tools do now. You see the effect that they have on a phase measurement. And when you look at those relative lines, you can get them closer together. And I would contend that even before listening to it, if you dial in things from 1,000 hertz and down and get them as close as you possibly can, that section of your system is going to sound magically better. It's not magic, it's science. We know it from doing all this analysis. It absolutely works when you go through and dial it in. Above that 1,000 hertz, you can still do these same practices, but if you notice it, the phase measurements get kind of jumbled as you get up high, especially if you remember the delay thing. You saw there's a whole bunch of raps and a whole bunch of mess going on up there. And it does get cleaner when you're playing only high frequencies, but it's still a little bit harder. But ultimately, I would contend that we should be listening to it and focusing on the magnitude response more than phase at that point. So there is no one magic answer to how do we tune a system. It depends. It depends on what part of it you're tuning. So in summary, all of this tuning stuff, we started off talking about the history of stereo and what was imaging and staging and all that stuff. That's what we started off. We wanted to get back to some magical illusion. If you remember, it was an illusion of spatial perspective. Right? That's what we were focused on. That's why we did the history. We needed to know where we were going. And from that, we determined the 3 pillars of tuning. And we learned about the importance of phase and timing. And ultimately, what we're looking for from this whole tuning process is something that's repeatable, something that we could do over and over and over again, and using the science behind this by looking at phase response, looking at frequency response, and understanding all of this, and of course level, the third pillar. By looking at all this very critically and analyzing the data, we can actually make this repeatable. But the last part of listening is something that we have to do. It's the fun part. Don't skip it. Don't skip the listening part. That's where the magic comes in. So, that was a lot of stuff. And I knew I'd run long, but I think it's okay. I'm going to jump out of the keynote now and start taking any questions, and I imagine there will be some. Actually, what do you think? Should I stay in the keynote in case I have to go back to a slide?
No, I think we'll be all right.
Well, if I need to, I'll jump back in.
Definitely a round of applause for Steve here. This is a tough subject, and he's really spent a lot of time making sure we're able to wrap our heads around phase. So
Thank you. Wrap our head around phase. It took me some time to get that one. All right, so lay them on me. What do you got, guys? What questions do you have? I imagine there's got to be some. So, yeah, I got to be honest with you guys. Now that technically the session's over and in the Q&A portion of it, when we first started thinking about how we were going to present this type of information, I don't want to speak for Rob and Kevin, but I was intimidated by it because the whole concept of phase is not something that we deal with normally. Most people don't think in the time relationship between drivers or anything like that, and being able to visualize that is very challenging. I found frequency response so much easier because I know that I move a slider up and things go up. I move a slider down and things go down, but I had no idea what was going on in time. And when we first launched the Tweak and the Fix, these are DSP processors that would alter things like time and frequency response. And people started asking about all-pass filtering, and I was like, oh God, I'm really not sure what an all-pass filter does. So we started looking into it, and when I got to the point where it's all about phase, it's all about time, right? Okay, that's starting to make sense, and we started digging into it. I realized that maybe there's a lot of people that don't know what it does. And as you start asking people, everyone's like, oh man, you guys need an all-pass filter on the Tweak. You got to have an all-pass. You got to have an all-pass. So we say, what does it do? And everyone's like, I don't know. Other people use it. It's like, okay, so a lot of people don't know. All right, I feel a little bit better. So we dug in and we tried to figure out an easier way of explaining it. And I hope this has helped. And ultimately, it is a key part of tuning, looking at that phase aspect.
All right, so we have a couple questions here. Andy Waymeyer, that name sounds familiar.
I don't know who that is.
He's asking where the crossover point, or what were the crossover points and slopes between the sub and the mid bass, if you happen to remember those.
God, I don't remember. I could pull up the file again, Andy. It's shame on me. I should have had that. So the truth is, when we do a lot of these tuning sessions, we're so focused on the actual measurements that we'll click into the field in the software, and we'll use up and down arrows and left and right arrows, and we'll watch the changes. We'll take a measurement. We'll put a filter on and we'll take a measurement, and then we'll change the filter and take another measurement, and we'll see the changes in the responses. And if we're going in the right direction, hey, we feel pretty good about it. But at the end, if the phase traces line up and the magnitude responses are doing what we want, we're pretty happy with it. We lock it and leave it. But I should have that information, and silly me, I don't. It was I created all the graphs for the training, and I forgot the data. So hey, by the way, Andy, it's great to have you here. Thank you so much for being a part of it.
We got a good question from Scott in the WebEx chat here. He says, is this harder with more than one sub to get things aligned?
It can get tricky. The fortunate thing is, in a lot of applications, the sub can almost be treated as a single entity. It's almost always going to be driven by the same channel anyway. So even if you do have two different positions of it, there's only so much you could do on the electronic side if it's a single channel that's driving it. Yes, you could do some goofy things on the wiring. Not a big fan of that because it gets a little weird when you get back into the tuning thing. But in general, we would consider the sub as one particular channel because it's almost always driven by one channel. So yeah, it would get trickier if you had, I know there's a lot of vehicles we put a sub on either side. And I think a lot of us know that is inherently challenging because first of all, they may be out of phase as they fire towards each other. It's probably not going to happen at very low frequencies. But yeah, it can be a challenge, and we would normally recommend trying to consolidate them into a single entity.
I find it not so much with multiple subs, but when you're using like a three-way, when the mid-bass driver has a very narrow pass band on it because of the way the high pass and the low pass filters kind of coincide with one another. That's where I find this really starts to come into play, and you really have to look at your phase traces to see what's going on there.
Absolutely. And it's funny, when we first started using this type of method of analyzing the phase response, a lot of people, when they listened to the cars after we were done, they said, wow, the transition, it's like magical. And we was like, yeah, it's like magical. It's like, no, it's not magical. It's science. It's repeatable. It's something we can measure and do over and over and over again when we get all those things lined up. And when you do that, it does sound magical because the results are tremendous. Now, I know for me, and I'm certain many of you guys are listening, the transition from the sub to the mid-bass for me is a very critical area because ultimately you want it to be cohesive. That impact should come together, not be separate. One of my home audio guys, he refers to it as a mud pie. You don't want a mud pie of information. You want it to be nice and tight and accurate. And it's always very difficult if you're only looking at the magnitude response to get it to be tight and accurate. It's this alignment of things and making sure things couple together and give the ultimate response both in magnitude and in time is when everything really comes together. So having visibility to the time aspect is huge.
Neil has a great point. He says it's further illustration how less is more in designing the system. The more speakers that you have and everything like that, the more possibilities for issues and more challenging for tuning there. And Neil, you're spot on. If the system design is not good and the install is not good, then you're just going to be chasing your tail down the line. So system design and install are definitely, you need to have those right before you try to get into this much detail.
I was glancing down in the chat there, and there was a comment made that I've never really looked at phase response because I use an RTA, and RTA can't show you phase. It shows the result of phase if you combine two drivers, but you don't necessarily know what caused any of those deviations. So if, let's just say we were doing a normal system and you had an RTA and you saw a big suck out, let's just pick 1,000 hertz just as a number, and you tried to take your EQ and boost it up and nothing happened, you could probably bet that there's some phase relationship that's causing that suck out, that's causing the problem, but you couldn't see it. You only saw the result of it. If you could have seen the phase, which is not that easy to do, which is kind of why we recommend using measurement systems so you can actually see that. If you could see the phase, it would jump out like we did with the subwoofer versus the mid-range, the mid-bass transition. We saw, actually, it was probably better when we looked at the full range spectrum left and right. That phase abnormality in the mid-range was evident when you looked at the phase response, but when you looked at the magnitude responses, they looked okay. It's only when we combine them that we saw a deviation, then we saw the phase wrap that was different for those two different traces. We tried polarity to flip it around, but that screwed up the other ends. By looking at the phase, we could say, oh yeah, of course, because it was already good, high and low. It was only bad in the middle, all pass, right? And it's a tough analogy of knowing what tool to use when you see what the problem is. And my analogy of a screw versus a nail, yeah, you could use an EQ to try to hammer in a screw, but what you ultimately want is a way of dialing it in better and use a screwdriver to make that connection, so to speak. A bad analogy, but I think you get where I'm coming from.
So interesting question on the WebEx chat from Phil, asking if it's hard to line all of this up using a center channel. His personal vehicle has a factory center channel location, but it's not used. Should he design the center into the system?
You can, and it gets trickier, and it's interesting that Andy's on the chat here as well, because if you do have access to using a really good quality center channel, you can technically use things like an upmixer, and instead of using a 2-channel system. Now, you remember the history of stereo. We're using 2-channel because the needle in the groove, we only had left and right. We didn't have the opportunity to use the minimum of 3, which is what was called for. With an upmixer, you could take a 2-channel signal and upmix it and have a multi-channel audio system. And using a really good upmixer, you can identify a specific channel for the center, for the left, for the right, and use all-pass filtering and other things to give really good results for both the left side and right side of a car. That'd be fantastic. There are some tricks that you can use, like left minus right, like that kind of stuff, or left plus right, that will create a center image in the software, including ours, that will allow some of that to happen. The phase traces are still important because they're all about arrival times, but now you have to be mindful that what you do on left will also affect what happens in the center, because they are, a shared channel to some extent. So I hope that answered it.
I think if you're aiming for a normal 2-channel setup, I personally wouldn't run the center channel. For me, the center channel really comes into play when you're trying to do multi-seat tuning, which is what these upmixers are doing. And typically when you're dealing with an upmixer, I know in my car, there was an all-pass filter on the passenger side door, which allowed the center to some flat with, acoustically, some flat with the right front speakers. So there's a lot of work that goes into that if you're going to try to attempt to make one. But I think if you're doing 2-channel, again, like what Neil mentioned earlier, keep it simple. As few speakers as possible. Get your 3 pillars done properly, and you'll think that speaker is playing even though it's not there.
Freaky when it happens really well. It really is freaky.
It is.
So.
It is.
So in my Jeep, actually, I don't have a center speaker. There's a grill that looks like it's there. And when people listen to the car, they're like, what speaker's in the middle? I said, there is no speaker in the middle. And I'll take a flat, a book or something. I'll lay it over the speaker and nothing changes. I'm like, how did you do that? PFM. So it's really cool. And, here's an interesting point to make about the session that we just concluded. I didn't give you any step-by-step of exactly what to do. And the truth be told, there is no step-by-step of exactly what you're going to do. But what you are able to do now is analyze things better. You know your tools better than you did before, I think, maybe. So you know what to look for, you know what to adjust, and you know how to do things. The process of how you go about doing that, there are some logical patterns to it, but I can't tell you first you do A, then you do B, then you do C, because there's lots of different ways of approaching this. There's also lots of different ways of tuning systems, but ultimately it all comes down to the same data, right? Magnitude, level, and phase. Those are the things that you're always going to be looking at, regardless of what processor you use, what speakers you use, all of it. That's the magic of all of this. And I get excited about that, learning the tools and knowing how to read the data. Whew. And what I think is really great is if you're using a measurement system like, REW or many of the other ones. We like REW because it's free, and you can share the files. Like if you're doing a measurement and you can't figure out what's going on, send the files over. To whoever you're working with. If it's JL Audio, send it to Kevin, Rob, myself, or any one of our tech guys, and we'll look at the data together. Said, you might want to try doing an all-pass filter here at 4K or whatever. We'll give you some advice looking at the data. However, if you're only using these measurement systems, if you're only using your hearing, all you have is it sounds weird around 4K. I can't really help you. You need to give me some data, and sharing that data is going to be great.
So Rodrigo says he wishes we would have talked more about the values and such of the all-pass filter applied on the examples at least there. One of the nice things is you can go in and add an all-pass filter and look what it's going to do electrically in some of the different measurement systems that are out there and available. So you can actually look to see what that value is going to do and what the different values are going to do. and kind of give you an idea of what to look at just by playing with it. And honestly, the more you mess with it, the better off you are, right? So the first time you do this and look at this, in fact, first time I really started looking at phase, it took me quite some time to really kind of nail down, and I would try a bunch of different things to go through and fix it. And now the more you do it, the easier it is to look at a certain area and say, hey, I recognize this now. I've done this a bunch of times and this fixed it here, or what have you. So the key thing is make sure if you make a change to something and it doesn't fix it, go back and then start fresh and make a different change. Don't just keep layering changes on top of one another, because you might get kind of deeper in the weeds than you want to be.
On. The other thing that I was worried about by getting too far into the specific values, not all software has tons of flexibility to make those kinds of changes. So what we did show is the varying Q. Our software does allow you to change Q. Others can allow you to change the type as well. So there's, much like a high pass or low pass filter have different types and slope rates. There are variabilities in all pass filters as well, but different software will allow different types of control. So what we wanted to show is just the general of what's happening with the shape of that, and how higher Q filters are going to get it closer to the center point, or whatever the frequency is that you've identified. I didn't want to get too focused on that, much like we didn't get too focused on different high pass and low pass filters, Butterworth, Linkwood, Triley, and all that other stuff. We just generalized it so we know the tool set. And using my tool analogy, I didn't tell you what size screwdriver. Was it number 1, number 2, number 3? But it's a screwdriver. It's a certain type of screwdriver. So that's the same type of mentality. They all have a similar functionality. Just pick the right one for the job. And visibility is key. And Kevin, everything you said, I would resonate and repeat, but we don't have time. So. I appreciate the extra time today, guys. As you can see, it's a pretty heavy topic. There's a lot that's gone into getting to this point as well. A lot of people have been asking us for a tuning class. Hey, you got to do a tuning class. It's like it's not that easy, because if you don't understand some of the background of it, it's real hard to come in and say, okay, we're going to analyze phase response. Oh my God, you kind of have to build up to it a little bit. And even this session, I can make a case that we should do it in 2 stages, but I can't find a good break point. So that's why we kind of force you into a longer session than normal. So. Jonathan, it's
questions about if REW is able to look at phase, and yes, it is. Whenever you run your impulse responses, you're able to line those up and see how they look in the phase domain, and how they align with one another and compare them to each other. REW, we use it a bunch. It's a great program. It's free, which is a big selling point. It is a little time consuming, because when you do make an adjustment, like if you add delay, you have to run another impulse response and make that comparison again. However, it's free, so it kind of makes it, it allows you to do it, and it doesn't cost anything. So really, it's just adds in maybe 10, 15 seconds of your time. Like I said, the first couple times you do it, because you make a change and it might not be the right change, you run an impulse response, and you make another one, you run another impulse response, and keep going and keep going. It may take you a little bit more time to go through and do this. However, as you get better and you start understanding and seeing what's going on, you'll probably minimize that quite a bit. So it is a great tool to use. To be able to go through and do it. And definitely, like Josh said, watch the tutorials, and you should be good to go with that.
We keep joking about REW being free, but he does take donations, and if you do use it, please give him a couple bucks, man. He's done incredible stuff. It's ridiculous that such an advanced program is out there at no charge. But, if you use it heavily, help him out, because he puts in a lot of time. If there's issues that you report in his forums, he's on it like within 10 minutes within your post. So take care of the guy if you're going to use his software.
In some of the development in some of our trainings, we use REW to capture some data, and there was some weirdness about it that, hey, it would be really cool if you could do this. And I kind of submitted it in, and almost immediately I got a response back, download the new version, see what you think. Oh my God! And he did it. He did it. He's fantastic. So I agree with Rob. If you do use it, click on that donate and help the guy out. He's a really nice guy and he's very responsive. He likes doing what he does. So.
Well, the questions have slowed down, and we have another session at, is it 10 today on Stealth Box, or at 1 o'clock Eastern today?
Yep.
Should we call it, or is there anything else we need to show?
Yeah, I think we'll call it. And just know if you guys have additional questions, we're available offline as well. You don't have to just do it here live, but anytime you want, just ping us an email or whatever it takes, and we'll do everything we can to help you through some of this stuff. And a couple of sections there, maybe you got a little bit more confusing. Fully expect some questions to come through, so let us know what we can do to help you. Thank you so much, everyone, for watching and giving us the extra time. We'll see you at the next session.